The dataset I have chosen is Uruguay's renewable energy consumption as a percentage of its total energy consumption for the period 1990 to 2018. This is taken from the World Bank website. The plot of the series is on the the left-hand side, and it shows an initial downward trend up until about 1999, and then a change point which then moves the trend upwards from then until 2018. The series doesn't appear to show any moving average, but does exhibit some AR behavior. There's no obvious seasonality and no changing variance. The plot on the left-hand side shows a strong positive correlation between each observation and its first lag. The correlation was calculated at 0.917, and the descriptive statistics as well are a mean of 45.57 and a range between 33.3 and 60.73 at its maximum. So to test the normality of the series, we did an ACF and PACF plot. ACF plot showed a slowly decaying pattern. PACF plot showed a very high correlation at the first lag. And the ADF test showed that this was not a normally distributed series. So we went with a log transformation, which yielded very little improvement. So then we reverted back to the raw series and did differencing. The first difference series showed a slight upward trend, but with a bit more variance, even though it had decent results on its ADF, KPPS, and PP tests. I still went with the second difference series, as that showed a flatter series with less variance and similar results on its ADF, KPPS, and PP test. So now we move to model specification, and as we can see from the ACF and PACF plots, there is 4 significant lags in the PACF and 1 or possibly 2 significant lags in the ACF. So from that we form 422 and 421 ARIMA models. With the EACF, the upper leftmost dot is 0, 1, and therefore its neighboring values are 021, 022, 121, and 122. And from the BIC table, the possible values for the model are P from 1 to 5 and Q1 for the top ranking model. There is a second ranking model which has the same parameters except Q may equal 2. However, that is not supported by any other model below it, so I've just chosen to go with the top ranking models, which are in this table on the left-hand side, and anything written in that red color are duplicates which appear across multiple sources. So this table on the left-hand side represents the candidate models, which we'll test further. The coefficients were tested for all the previously identified models, and all models except for ARIMA 021 and ARIMA 122 contained insignificant coefficients. ARIMA 122 is ranked 4th on the AIC and BIC tables, and so that was rejected as a further candidate model. ARIMA 422 did have the least errors. However, it was quite low down the AIC and BIC tables, and it was a large model, and on the principle of parsimony, that was rejected as a candidate model as well. So for residual analysis, we will proceed with ARIMA 021. So in our residual analysis, we find that in the time series plot, there's a flat mean level. The histogram doesn't reveal any outliers. The ACF plot shows no significance of any residuals. All lags are above the confidence levels in the Jung-Box plot, and the Shapiro-Wilk and Jung-Box test have p-values that suggest that we cannot reject the normalities of the series. So the ARIMA model 021 was deemed appropriate for use for forecasting. Note that overfitting was not performed, as the neighbouring models were already in the initial set of models identified and were deemed unsuitable for further analysis. So the forecast produced from the ARIMA 021 model is as follows, and it shows a slight upward trend for the next 10 observations. And the details of those are in the table on the right hand side.